All right, we're going to run through some practice questions on potential energy and electric potential. So first of all, I put a list of our current equations, at least for this unit or this week, as well as some constants. I will have these on quizzes. Just please make sure that you are keeping an ongoing list of important constants as well as all of the equations. Okay. So to start off, we're going to do a couple of easy ones. I know I run through these pretty quickly. This is also why I have uploaded the documents, so you can it's actually better for you to go through them by yourself. And then if you get stuck, to refer to these videos or the answers in order to kind of check to see where you get lost. All right, I do know that it helps to see somebody do some practice examples, but to really truly learn how to do them, you need to do the calculations yourself. So you can watch me run through them and then try them on your own, as well as a lot of these are similar to ones that you're going to see in your homework for this week. Okay, so we'll start with some easy ones. For question 1, suppose you have a 12-volt motorcycle battery that can move 5,000 coulombs of charge and a 12-volt car battery that could move 60,000 coulombs of charge. How much energy does each deliver? So this is kind of a different question. It's asking two separate questions. So we have an electric potential, right, which is symbol V, and then we have a charge, which is Q. Sorry for my writing. And then we have a separate voltage and a separate charge. So we're doing two separate calculations here. So for this one, our potential energy, we can just have, and again, we are using U. PE is very common for potential energy. U is equal to our potential times that charge. So you're essentially just multiplying the two of them together in order to get that number. So to me, this is a nice, easy one-step, one-point type of a question. Question number 2, a 12-volt battery is connected to two parallel plates. Okay, and so again, as you read things, I know some of you like to print out some of those work. I always recommend people highlighting or making notes on the question as they read them. Okay, so we have two parallel plates that are separated by a distance, okay, and centimeters, we got to change to meters. This creates a uniform electric field between the two plates. Find the magnitude of the electric field. Okay, so we're determining E here. All right, and so last week we were looking at electric fields of point charges. This time we have plates. Okay, so in this case, we can use this equation here. And then as always, if you ever get stuck, write out your given information. Okay, so 12 volts, that's your electric potential. It's one of the only ones that we'll ever use that the symbol and the symbol for the unit are the same. So potential, which is also a voltage, so our potential is in volts. Okay, well, our potential difference is the voltage, but both are measured in volts. So we have a 12 volt, and then we have a distance, which we're going to change this to 0.5 times 10 to the negative 2, or just move it over 2 more decimal places. And then it is asking us for a field. So now that we have multiple equations to look at or to choose from, it is a really good idea to write out your given information unless it's obvious. Okay, so now I can see that I've got V, I've got D, and I'm looking for E, so it makes choosing an equation so much easier. All right, so I'm going to rearrange my equation, plug in my values, and I end up with 2,400 volts per meter. Okay, and I showed you in the notes how your electric field can be measured in volts per meter or newtons per coulomb. Okay, question number 3. When a 4 coulomb charge, that's a big charge, 4 coulomb charge moves from point A to point B in an electric field, the potential energy is decreased by 76 joules. What is the potential difference? Okay, so once again, we are looking at our values. So we know we have a charge here of 4 coulombs. Okay, and it's moving from point A to B, which is decreased by 76. So our change in potential is going to be, in this case, a negative 76. And again, that's just showing that we're losing it versus gaining it. Okay, what is the potential differences between the 2 points? And I apologize, this should be our change in U. Okay, because this was our energy. And I just explained how you need to be careful of energy versus potential. And I just made that mistake, so I apologize. So now we're looking at our potential difference. Okay, so we can determine that we've got our change in energy, and if our energy is decreasing, our potential is also going to decrease, which is, whoops, too quick, which is why we have a negative. So we end up with negative 19 volts. Okay, so what distance? So we're determining what D is. Should 2 plates be placed who are connected to a 9-volt battery, there's our potential, to produce a 75 Newton per Coulomb field. Okay, so in this case, it is actually giving us our voltage and our electric field. So we can once again plug our numbers in and see that it should be 0.12 meters or 12 centimeters. All right, so question number 5, I use this one purposefully because we've got 4 different questions for one situation. All right, and the really cool part about physics is, well, what I think is the really cool part is that as long as you're following the rules and using the correct variables, there's always more than one way to answer a question. All right, so I'm going to run through these and I'm going to kind of point out different ways that we could have actually done this. Okay, so to start off, an electron, and again, anytime it is given something like an electron or a proton, we know the charge, right, is sitting 10 millimeters. And so that 10 millimeters is going to be 0.01 meters away from a small object of -5 microcoulombs. So that's -5 times 10 to the -6 coulombs. What what force does the electron experience? Is it attractive or repulsive? Well, already we know if this is negative, electron is negative, it is going to be a repulsive force. All right, and then we're going to use our force equation, which is K Q1 Q2 over R squared. We've been doing this a whole bunch, okay? So if you plug in your K value, your charge of an electron, your charge here with coulombs, not negative or not microcoulombs, and then don't forget to square this distance at the bottom here, we end up with an answer of 7.19 times 10 to the -11. Oh my goodness. Where'd it go? There we go. -11 newtons. All right. So next question says, what is the strength of the electric field provided by the source charge at this point? And so the electric field of that source charge, remember we're going to use our electric field equation, which is KQ over R squared. Now, if you are confident in this answer here and understand that, the difference between this question and this question is that the Coulomb, or multiplying by the charge of the electrons. And so you can either plug everything back in again or kind of do the shorter version. I'm not going to show you guys that, but if you understand what I'm talking about. Okay, and so this case we get 4.50 with a little bit of rounding. I'm keeping 3 sig figs for all these, times 10 to the 8, and again that's newtons per coulomb, or it could be represented as volts per meter. Okay. Determine the electric potential of the source charge at this point. So here's the fun part. Okay, so the electric potential from the source charge, we are going to use KQ over R. All right, but if you notice, we already have E. Okay, and E is KQR squared, but we also know that V is E times D, right? And so we're actually doing the same thing here, where we could use this electric field and multiply it by that distance, or we could use all of the fresh numbers and plug it into this equation here. Either way, you're going to get the same answer. My suggestion, although it's a little more tedious, I personally on an exam would use this one solely because I'm using values that I haven't manipulated yet. Let's say by chance I happen to make a mistake typing that into my calculator, and then if I use it again, that kind of amplifies my answer or my mistake. Although when you show your work on your quizzes and submit that work shown, I can see that and I'll award points where applicable. So using this one here is a little bit more work, but you're not worried about whether or not you made a mistake here, unless you're just super confident in your calculations, which I'm sure many of you are. Either case, you end up with 4.50 times 10 to the 6. And again, our potential difference is measured in volts for that one. Okay. Now, once again, we've got two choices here. Determine the potential energy stored in the field. Okay, we know our potential energy equation is K Q1 Q2 over R. Whoa, ran out of space. Over R. Okay, but we also know that our potential is our potential energy divided by Q. And so our potential energy could be our potential times that charge. So once again, you have a choice. You could do the easier one, assuming that your answer here was correct, or you can use the original values from the question and just recalculate. Once again, either way, you should end up with 7.20 times 10 to the negative 13. And in this case, it is energy, and energy is measured in joules. All right, so that is walking you through pretty much every equation that we've used in this unit or in this week. And again, you've got some choices on how you do that. As long as you follow the rules in terms of the laws of physics, but also what variables are placed where, you can make some different choices on how you calculate that. Okay? All right. So our last question here, this one stumps many, many, many people. And it's for a reason, because you look at this and you're thinking to yourself, wow, I don't have a lot of information. So let's go ahead and read it here. So what is the change in electric potential energy? Oh, just kidding. This question is not the one that I was referring to. This one is actually quite straightforward. It's the next question that I was referring to. I'm getting ahead of myself, guys. Sorry. So what is the change in electric potential energy? Okay, so we're looking at delta U of a charge, a test charge. So that is Q that moves through an electric field from point A to point B. So in this case, we are going to look at that change in electric potential times our charge in order to get the change of an electric potential energy. We just plug those numbers in. Remember, your change in potential, anytime we have a change in, okay, you've probably done this in chemistry before, it's always final minus initial. Okay, so our final would have been 9 volts minus our initial, which is 24 volts. And so that's how we get that negative, and that negative means we're losing that energy. Okay. And so that would get plugged in for that value there. Okay, so, whoa. Not sure what's going on here. There we go. So this is the one I was referring to. Okay, so this one stumps many, many people. Calculate the final speed. Okay, well, first of all is velocity of a proton, and this is a lowercase v, sorry, of a proton that accelerates from rest through a potential difference of 120 volts. Okay, so what we're doing here, first of all, we have a proton. So a proton, we know its charge, all right? And we know that it's accelerating from rest. So our change in velocity is going to be final minus initial. Our initial is 0. and we have a potential difference. So let's start by just writing out what we know. Okay, so we know Q is 1.6 times 10 to the negative 19 coulombs. We know that our delta V, or change in potential, or potential difference, is 120 volts. Okay, now it's accelerated, so that means we're actually losing this. So technically that should be a negative 120 volts because that potential is turning into that speed. Okay, we're trying to find our velocity. Okay, so this is an energy question, and I used to tell my 121s, in an energy question, if you're not given a whole lot, you need to think about the situation. Okay, so if you think back to, we have this proton and it is being accelerated, right? And so this is going to be a conservation of energy because we're looking for speed, and the only time we've even talked about speed is when we've talked about kinetic energy. And we know our change in potential energy and our change in kinetic energy needs to equal 0 because the total energy of the system remains constant. So our change in potential energy is going to equal the change in kinetic energy. And so in this case, our okay. So kinetic energy, for those of you who do not remember, our kinetic energy is 1/2 mv squared. So I would add that to your equation list. You will need it for Expert TA as well as your quiz this week, although I'll provide it at the beginning of the quiz. So now we have, we can plug in our values here, right? We have negative 120. We've got 1.6 times 10 to the negative 19 equals, we've got that negative there still, which is going to cancel out those two negatives, right? And then we need to know the mass of a proton. Okay, I put that in the information at the beginning of this presentation. And so the mass of a proton is 1.67 times 10 to the negative 27 kilograms. And then we have our velocity squared. Okay. So please add that to your list of constants, that mass of a proton and mass of an electron. Okay. So in this case, I know you guys are really advanced in math, but some of you have just not done this math in a while. All right. And so when you're doing this, okay, everybody likes to deal with that exponent first. Okay, and that is fine when we're just solving for this. If this was an actual number, you would have to do that. But we're doing the reverse of our order of operations. We actually need to isolate that v squared before we can take the square root. All right, so our negatives are going to cancel. We're going to bring this 2 up over here. Whoa. And I just lost all my work. Anyways, we're going to bring this 2 up over here, and then we're going to divide out our mass. And then that way we isolate our v squared. At the very end, the last thing you should be doing in this question is taking the square root. Okay, and so if you do all of your calculations correctly, I ended up with 1.07 times 10 to the 5 meters per second as my final answer. Now, when I get these answers, it kind of, again, depends on how you round, as long as you're within reason of that answer. Like if you're ending up with 3.5 times 10 to the 5, then obviously we did something different. But 1.1-ish times 10 to the 5 meters per second for that velocity. Okay? So hopefully this is going to help you work your way through those Expert TA questions. As I mentioned, please make sure that you are working these problems on your own. If we were an in-person class, I would have you actually work together on these problems, not just watch me do them. So in a fully online class, it's important not just to look at these and let them go because they weren't worth points, but to practice. All right. The more you practice, the better you're going to be at this, just like a sport, just like an instrument, just like a play, anything that you do. The more repetition, the easier it's going to be, and the less stressful it will be when you get to taking that quiz at the end of the week. Okay. Hope that helps, and have a great week.